10 minutes for questions to the panelists from members of the Assembly. At the conclusion of the briefing, we will allow for public comment with 2 minutes allotted to each speaker. If we're not overwhelmed by the number of speakers, we might have to reduce it to 1 minute, but we'll try for 2. I want to extend my gratitude to all the presenters who took time from their busy schedules to be here today. This is a gathering of luminaries, and your presence today speaks to your dedication to guiding California to a sustainable future. Thank you all very much. Now it is my pleasure to call the first panel on balancing demand management and diverse renewables. I'm going to introduce them, and then I will call on Jennifer Chamberlain to start. We have Max Way, research scientist, energy analyst, and environmental impacts division at Lawrence Berkeley National Lab, which is truly a gem of in California in terms of looking at our clean energy future. Jennifer Chamberlain is a board member of the California Efficiency Demand Management Council, and then Colin Kushney is vice president of Power Supply, Southern California Edison, and I misspoke. Max Way is our first speaker, again, from Lawrence Berkeley National Lab. Max.
Thank you very much. I would like to thank Assembly.
Your microphone?
Is that better?
Yes.
Okay, sorry. I'd like to thank Assemblymember Quirk for the opportunity to speak to the panel today, and I'd also like to congratulate you on recently receiving the California Council on Science and Technology's Science in the Public Service Award, which is given to a legislature who has provided exceptional service on promoting good policy informed by science. So, congratulations.
It's my job.
Okay, so I am here to give an overview.
Speak into the microphone.
Right. Sorry.
Okay.
I'm here to give an overview, and I wanted to start with this slide, which is just a system depiction. And I just wanted to highlight several important features of this diagram. So, of course, we have generation, T&D, demand. We're increasingly seeing the need for storage at different timescales, and, of course, underpinning this are markets and regulations. I just want to focus on the interconnectedness of this system with other systems, several other systems, at least half a dozen. First of all, there's the connection with other grids outside of the state, so CAISO may have relationships with other grids in the western US. Secondly, there's interactions with the climate system in many different ways. The climate system can increase demand on the demand side, with hotter summers leading to greater air conditioning demand. It can impinge on the transmission and distribution side in terms of efficiencies, and also on the thermal generation side. You can get interactions with the water system and the hydrological cycles. We have seen from our modeling that in conjunction with UC Irvine that there's much more variability, and Scripps, there's much more variability year to year in hydro availability in the state, and that snowmelt is happening earlier and earlier in the season. There's an interaction with other economic sectors which are partially shown here. So there's the interaction with the industrial sector and the transportation sector, in which there will be more electric demand anticipated as more end uses become electrified, such as building electric heating and industrial heating. There's the interaction with the natural gas system, which has its own parallel system, which we won't be discussing so much, or I won't be discussing so much, but it's just something very important to keep in mind. How does that interact with the electricity system? There's interaction with ecosystems. Wildfires are growing. There's also, finally, the most important interaction, which is with people. Like, what do people need, and how can we provide safety and adequacy of services, reliable services, and comfort to all the citizens of the state. So just to describe some of the recent trends, obviously on the generation side, we're seeing a tremendous increase in the amount of solar, both central and rooftop solar. And that is leading to, that's been a great success, but it's also leading to challenges in the integration of increasing amounts of solar. And so I've been asked just to describe the duck curve, which I think many of you are familiar with. So this is just showing the sharply falling costs of solar over time. This is from LBL's Tracking the Sun study. And this is just a trend showing the dramatic increase. I don't know if you can see, but it's the yellow bars in this bar chart on the right for centralized solar, and orange is distributed solar. So for the duck curve, the real issue for the duck curve is how to integrate increasing amounts of solar into the system. So as you get, so the top curve is, you can think of that as just the load in the system. So there's going to be a peak typically in the morning times as people wake up, and in the afternoon as people come home. And so there are those peaks. As you bring more solar onto the system, the load, which is served by non-solar assets, will take a big drop. So you will introduce a belly in the duck curve. So this shape here forms a duck shape, and it's really the shape of the non-solar and non-wind resources that are required. So as you bring on more solar generation,